I'd like to welcome one and all to this first in a series of videos presented by Current, powered by GE. We are located in Cleveland, Ohio, and we're coming to you from the Institute at Nela Park. I will be the speaker for our first one, LED Basics. My name is David Korow, and I'm one of the staff instructors here at the Institute, and I'm very happy to be your presenter. The contents of this webinar is shown on this page. Many topics will be explored. This page will give you a quick summary of where the different topics begin and end, as well as the begin time and end time, so that when you're viewing this as a video, you'll be able to go to any individual subjects and find them quickly by referring back to this page. By 2030, the U.S. Department of Energy says that LEDs will save the U.S. approximately $15 billion in electricity. To say that LEDs are causing an evolution in lighting, I think, is to underplay their significance. LEDs are causing a revolution in the industry across the world, and the question that should be asked isn't if I'm going to move to LEDs. The proper question is, when will I move to LEDs? LEDs have been around for decades and decades. The acronym LED stands for Light Emitting Diode, and the very first visible LED was created by our Dr. Nick Koloniak, a scientist working at General Electric in 1962. Dr. Nick is known as the father of the red LED. Dr. Nakamura, in the late 70s, invented the first high-efficiency green light LED, and then he, along with two other colleagues, Amano and Akasaki, invented the high-efficiency blue LED, for which they won the Nobel Prize in Physics in 2014. Now that we have high-efficiency red, green, and blue LEDs, we can generate any shade of white or any color of the rainbow that we like. Where do LEDs come from? Well, they start out as a silicon wafer. I think of the wafer as a ping pong paddle, about that size, 6 to 8 inches in diameter, and on that ping pong paddle sized wafer, LEDs are actually epitaxially grown layer by layer until the chips are actually formed. They're made of two different materials, N material and P material, and by stacking those two materials, we make a semiconductor device called a light emitting diode. Each of those LEDs, or at this stage of their development, they are called dies. Each die is liberated from the disc either with a diamond saw or by snapping it off the disc. Dies are sorted or binned by voltage, lumens, and color temperature. Materials are added to the LED to shift its blue color into red, green, blue, or the three primary colors, and by adjusting the phosphor used on the blue LED, any color or shade of white can be achieved. Chips are then packaged, leads are attached, and at this point, the LED manufacturer, typically in China, is able to now sell the LEDs. LEDs are then bought by manufacturers, and the manufacturer then adds a driver, optics, and an assembly, and create the final system, be it a screw-in light bulb or a luminaire that would be used outdoors or in a factory or warehouse. This is a schematic of an LED. You'll notice that it has a plus side and a minus side, so therefore it is a polarized device. The anode is the positive side, the cathode is the negative side, and if a battery is connected, as shown here, with a switch and a resistor to limit the current, we can now make an LED flashlight. Red, green, blue LEDs excite the tri-stimulus characteristic of the cones that are in the human eye. When the appropriate percentage of red, green, and blue light are present, human beings see white light. As you see in the first object here on this screen, when you combine those three beams, you can approximate any shade of white that you like. The weakness of this system is you need 3 chips to generate 1 pixel of white. If any one of those 3 colors shift over time, the white will shift in color. So there is a problem with robustness and complications to overcome this weakness, and therefore most LEDs that are used to generate white light in today's industry start out as a blue LED chip. Over that chip is placed phosphor. When the blue light goes through the phosphor, some of that blue light is changed into green and red light, and the combination of RGB from that single device is how we produce white light. This number 2 choice is the primary way that white LEDs are manufactured and sold today. Option 2 has the phosphor directly on the chip. It does cause the phosphor to age, and that's what will cause color shift and degradation of lumens. This is due to the fact that the chip itself can run very, very hot. Oftentimes that chip will run over 200 degrees Fahrenheit or hotter than boiling water. There's a third way to create a white light source, and that's shown in figure 3 at the bottom of the page. This approach uses a blue LED similar to the LED used in option 2, but instead of applying the phosphor directly to the chip, the phosphor is now applied to a remote surface. That remote surface can be the lens, or it can be a suspended surface above the LED. This approach prevents the phosphor from overheating and therefore greatly extends the life of the product. More research is being done today in remote phosphor products. The thought is that additional performance gains can be had by applying this technology. If we talk about LEDs, we've got to talk about LED drivers. Now, for most of us, an LED driver is simply a black box with wires coming out of it. There's going to be a white wire and a black wire. That would be your input. And then the output is going to be your DC voltage. Most LED systems are wired in either series parallel or series parallel, like I have shown here. This array has 5 LEDs. Each of those LEDs is approximately 3 volts. 5 times 3 is 15 volts. So this driver is probably about a 15-volt driver, and then depending on how much current is needed to run these LEDs, the driver can then be sized appropriately. A driver is simply a device that changes AC into DC, and the DC level is typically lower than the AC voltage coming in. So in this case, you might have 120 volts going in, and you might only have 15 volts coming out of this particular driver. The driver, in addition to changing AC to DC, also limits the current, which is one of the ways that we can maintain the proper power in the system, and therefore junction temperature. Now, the junction temperature is the point between that N and P material, actually where the photons are generated as electrons move from the negative to the positive side of the semiconductor material. Maintaining that junction temperature is absolutely critical to maintain the published life of the product. Also, the driver will determine whether there is dimming capability. Now, dimming can happen either by changing the magnitude of the voltage coming into the black and white wire. That would be line voltage dimming or phase dimming, sometimes referred to as triac dimming. And typically in commercial applications, dimming is done by attaching a 0 to 10 volt DC supply to a purple and gray wire coming out of the driver. By changing the level of that voltage, 0 being full dim, 10 volts being full brightness, full dimmability can be achieved. Dimming typically is anywhere from 100% down to 1%. That is becoming more and more the standard in the industry. I mentioned heat, and heat is something that needs to be managed by the product design. So the design of the lighting device needs to include a way to get the heat from the LED itself out to the outer world, and that is typically done with an external heat sink as shown in the diagram here. The die itself actually is sitting on a board. That board is then going through a number of different interfaces. It finally hits the external heat sink. Air blows across that heat sink, and we have a junction temperature that operates at the proper temperature. Once again, to achieve the long design life that's specified on a cut sheet, we as an end user, or certainly we as a designer, have to make sure that we do not exceed the maximum temperature of that LED. The photo in the upper left of this page shows a lamp with heat sinks, and those are necessary to achieve the required cooling. Some of the benefits of LEDs I'd like to go through next, and they are 10, and we will look at those on the next page. LEDs are very, very efficient. Their efficacy, lumens per watt, is excellent. We now are seeing commercial fixtures used in high bay and warehouses at 200 lumens per watt, so energy efficiency is something that makes LEDs very attractive. Low lead in mercury or no lead in mercury is common. So the whole issue with EPA required disposal is eliminated with LEDs. Life of LED systems are now typically running anywhere from 25 to 100,000 hours. 100,000 hours, if you think of it in terms of daily usage, 12 hours a day, 7 days a week, 365 days a year, 100,000 hour life equates to a 20-year usable life. That's 20 years with essentially no failures of the LEDs. Excellent beam control lets us put the light where we want it. Virtually maintenance free, meaning once you put it in, you can forget about it. And because of the low power usage, very, very reduced carbon footprint compared to other light sources. Spectral content is something that's being changed either manually or through control, so we can change the color temperature or the shade of white. And there certainly are a lot of color changing LEDs on the marketplace where you can literally move it through red, green, blue, or any myriad of other color combinations. It's a very durable device because there are no metal filaments or typically any glass to break. They are dimmable. They typically are instant on, and in many cases the on-off cycle does not matter. I have to say that with some caveat. Recent testing from the Lighting Research Center is showing that rapid on-off cycle can cause early failure of LEDs. That data is coming in as we speak, and as we learn more about it, we will have to address that in the life ratings of these products. Finally, essentially no UV and no IR coming out of these lamps beam, so you don't have to worry about the problems of ultraviolet light damaging materials that are being illuminated by it, or heating the space by putting infrared or IR in the beam. Now once again, that heat sink on the back of the lamp, on this one in the upper right, is smooth, but that is a metal housing on that lamp, and it is metal because the heat is conducted to the metal, and then as the air goes across the metal, the temperature is maintained for that junction. I mentioned efficacy a moment ago, and efficacy is something that is very important for energy savings. The better the efficacy, the more savings we have. You'll notice incandescent and halogen at the lower left corner, around 15 to 30 lumens per watt. LED is clearly lapping every other product. The latest data from the Design Lights Consortium, which includes about 350,000 SKUs, is showing the LED lumen level to range between 50 and 163 lumens, and the average to be 99. So 99 lumens per watt is the average for the 350,000 products that are on the qualified products list of the DLC. This graph, I should mention, is mean lumens, so it's mean lumens per watt. This is the range of lumens you would expect at about 50% of rated life. CFL are lower efficacy than LED. Fluorescent metal halide and high pressure sodium are similar at the low end LED, but LED is now twice as good as our very best metal halide and high pressure sodium. Very impressive range of performance with LEDs, and the LED bar continues to march to the right where all the other bars are pretty much static. Nothing's happening with those. The next thing we want to talk about is LED life ratings. Traditional lighting products, be they halogen, fluorescent, HID, compact fluorescent, incandescent, have a mortality rating based at the time when 50% of a large distribution fails. So, for instance, I put 300 metal halide lamps in. They are 20,000 hour rated. What you can expect is half, or 150, of those 300 lamps to have failed at the rated life, which in this case is 20,000 hours. So when we talk about B50, that means the point in time where 50% of the population has failed. B10 would mean the point in time where 10% have failed. Standard lamps or traditional lamps fail per a curve like this, and the life rating basically tells you the average life or where you expect 50% of the product to have failed. This is to be contrasted with LED. Now, LED life is not based on mortality. It's actually based on light output dropping to a lower level. And that lower level is referred to initial minus end of life. And the difference between the initial lumens and end of life is typically 30%. and it's referred to as L70 or lumens 70. So rated life is based on the point in time where the initial lumens have dropped to 70% of that rating, or they've dropped 30%, or L70. When they hit L70, that's where rated life is published, and that is where you as an end user would replace the lamps. Since it does not deal with failure, there is not a B rating. It would be B0 at 100% rated life. Now, there is nothing perfect in the world, so B0 is a stretch. There is certainly going to be some percentage failed at 100% rated life, but the percentage fail is going to be minuscule compared to what we're used to with standard traditional lamps. Let's talk about DLC, the Design Lights Consortium, and utility rebates and incentives. The Design Lights Consortium is a group of non-government organization, or NGO, utilities and energy efficiency programs across the United States and Canada that have formed an organization that pretty much mirrors the DOE EPA Energy Star program. Now, since Energy Star is for residential and consumer products, there was a big void in the industry to identify quality products with good performance that were used in commercial and industrial applications, and that's why DLC was created. The DLC organization is identical across borders, so Canada and U.S. have exactly the same program. Utilities and energy efficiency programs adopt this DLC Qualified Products List, or QPL, as a list of products that the utilities or energy efficiency programs, would actually offer rebates on. As of April 10th, there are about 1,800 companies with products on the DLC QPL, Qualified Products List, that make up 351,000 products in 75 primary user groups. Now, of those 75 primary use groups, the top 12 account for 80% of the products. There's a lot of products out there that have utility rebates and incentives attached to them. Our challenge is to find out if our utility actually is using the QPL, and if they have an active program, how much money's left in the program, and if they are offering rebates and incentives for a product that you are actually interested in buying. Two programs I'd like to talk about that allow you to get a real-world view of how LED lamps and fixtures actually work are what I want to present now. The first program I want to talk about is called CALIPER, which is from the Department of Energy from the U.S. government. The DOE actually anonymously goes out into the world. They purchase LED products, be they light bulbs or fixtures. They test them up to 100 hours, and then they generate reports called CALIPER reports. Manufacturers' names, model numbers, number of lamps actually tested, number of fixtures tested are recorded in the CALIPER reports, as well as comparison to legacy technology. These reports can be very useful in determining which LED is proper for your particular application. A second program, which is shown here called Gateway, takes it to the next level and actually takes LEDs that are bought anonymously and puts them in actual world applications. Every 1,000 hours, these products are tested and the data is recorded, and at the end of approximately 1.5 years of testing, either in a retail application or on a bridge going across a river or in an actual warehouse, data is then accumulated, presented in a Gateway report. Now, the Gateway reports are also generated by the U.S. Department of Energy and available for you to peruse. There is no password or username needed to get to these. Simplest way to find CALIPER or Gateway reports is to simply go to Google, type in DOE CALIPER or DOE Gateway, and those reports will be available to you as PDF downloads. These are excellent, non-biased reports that give you an insight into where the industry is in any particular portion of the market that's being served. Let's move on to our catalog. Our catalog is today housed on a website, www.led.com, and that catalog will allow you to find any of the products that you would want from General Electric. Looking at this screen, you'll see the screen capture of our home page. So if you go to led.com, you'll pull up the current Powered by GE page. You'll see About, you'll see Careers, and you'll see Products. Products opens up a pull-down menu. What I'm going to do now is walk through that pull-down menu and summarize all the products that General Electric currently has in its portfolio of LED lamps and fixtures. Looking down the left-hand column of this page, you'll see that we have indoor, outdoor, hazardous, signage, controls, refrigeration display, and so on. These are major categories of fixtures. If you click on the indoor fixture link, it will open up the pull-down menu in the gray, which shows you all the different categories of indoor fixtures that we have. Recessed, recessed multiple, surface mount, strip fixture, suspended, and so on. Each one of these fixtures is available in a myriad of different layouts, different sizes, different lumen levels, different color temperatures, different color renderings. This is really just meant to show you the 8,500 different fixtures that we have and give you an idea of the breadth and depth of our product line. If I go to the next screen, we'll move to outdoor fixtures. Outdoor fixtures are made up of these different subcategories: street, area, post top, parking garage, flood, and so on. Each one of these categories also includes many different iterations. Street and roadway, as you might guess, would be Cobra heads. It also includes a high mass that replaces 1,000-watt high-pressure sodium. Within the family, we have good, better, best. These are all DLC listed. They are RoS compliant, meaning essentially no lead, no mercury, no cadmium. They are all IP66 or IP65 rated for outdoor use. And the last category you see, poles and brackets, we do offer that also in our catalog. So you can get the entire installation ordered from one company, General Electric, and have everything on site to do the install. As we move into hazardous location, signage, and so on, you'll notice that all these categories also include a myriad of different fixtures. I am summarizing them here. The hazardous location come in two different variations. Signage, we have backlit, we have recessed, we have surface lit LED. Refrigeration display, we have freezer case, we have open case, we have 4-foot, we have 8-foot. LED lamps and modules, those are our family of screw-in lamps that would replace your compact fluorescent or possibly your halogen or HID screw-in lamps. A full family of those that are Energy Star. We have the largest supply of Type A, Type B, Type C LED tubes and refit solutions. We also have a transportation product line that includes both railway as well as roadway control signals, such as crosswalk signals, stoplights, red, yellow, green, as well as railway signals. We have a line of horticultural LEDs for growing plants, and then finally a full line of drivers for these LEDs. I'd like to conclude the seminar with a summary, and that summary is going to take the shape of a quiz. Hopefully, after listening to the seminar so far, you'll be able to answer these questions. So I'm going to give you about a minute here. Read through the questions, jot down an answer. I'll come back in about 60 seconds, and we will go through the answers. Well, welcome back. Hopefully you've got answers to these questions, and let me just pull the answers in and we'll talk through them. Who invented the first visible LED? Well, you'll remember that was done by Dr. Nikoloniak while he was working for General Electric in 1962. LEDs are energized by AC or DC. Give an example of an AC and DC source. I think we talked about LEDs are DC, meaning they run off of drivers, and an example of a AC source would be the utility that generates the power that comes out of the wall socket. What are the three primary colors that make up white light. Red, green, and blue. Remember, those are the first way that we started making white light was by combining those 3 beams from 3 separate LEDs. Now we typically do it with a blue or purple LED with phosphor. Do LEDs get hot? Why do they get hot and how hot? And how do we manage the heat? LEDs do get hot, and it's actually the junction in the chip that gets hot. Also, it's due to the driver getting hot, so there's actually 2 heat sources in an LED luminaire or light bulb. Heat is managed with what? That metal heat sink with the cooling fins. Now, the cooling fins are passive. We also can manage heat with a fan. And some of our screw-in HID LED replacement lamps do have active fans in them. Number 5, name 5 benefits of LED lighting. Well, we went through those, and I've got them listed there. Hopefully you were able to hit those 5. What's the meaning of B10? What's the meaning of B50? B10 means 10% failure at a time. B50, which is used for standard mortality on all products except LED, means that at that time 50% will be failed. Most LEDs do not carry a B number because they're rated on lumen maintenance as their failure mechanism. There's one example where B10 does apply to LEDs, and that is with our HID LED replacement lamps. And because of the fan, those lamps are actually rated at 50,000 hours B10, which means that at 50,000 hours, you can expect 10% of the fans to have failed, which pretty much equates to the product failing, particularly if it's in an enclosed fixture. Name 2 rebate or incentive organizations. Which one's a non-government organization? Well, we talked about Energy Star and we talked about Design Lights. Design Lights Consortium is an NGO. Energy Star is Department of Energy, EPA. Name the DOE LED program that document LED performance. Caliper and Gateway. Those are 2 DOE programs that you can Google on the internet and pull up actual real-life data, either 100-hour data in Caliper or 1,800-hour data, year-and-a-half data on the Gateway program. Both of those are on the DOE website. And then finally, what is GE's LED website? That's an easy one. www.led.com. That's something I think we can all remember. So with that, I'm going to conclude our seminar. Thank you so much for joining us. We will be doing a series of these seminars to help inform you on subjects that we feel have been told are of interest to you. All the best to you. Have a wonderful week, and stay tuned for our next webinar. This is David Korow at the GE Institute in Cleveland, Ohio, signing off for now.